Good afternoon, everyone. It's my great pleasure to present my recent research here. And in this annual theory meeting, there are only 2 composite Higgs talks and one given by Zhang yesterday. And I also noticed that there is no talk with whose title involves supersymmetry. And yeah, in this talk, I will discuss something from a very different perspective compared to yesterday's talk by Zhang, because I will talk about UV completion. Yeah. And this is based on working collaboration with and from NTHU, and one short paper has already come out, and we are also planning a longer paper which includes more detail. Okay, and you might know that composite Higgs is motivated by the naturalist issue, and here I will give a very brief recap of 2 main pillars of modern composite Higgs models. And first is Higgs arises as a pseudo-Lamborghini boson. And the basic setup is as follows. And for simplicity, let's consider 2 sectors, composite sector and elementary sector. And let us note the existence of 2 scales called lambda UV and M star, which represent boundaries between different effective field theories. And lambda UV can be imagined as the scale where flavor dynamics is generated. And at this very high scale, lambda UV, the composite sector, the whole theory is supposed to sit close to a renormalization group fixed point. And the composite sector of the theory is supposed to exhibit an exact global symmetry called G. And when we evolve the theory down from lambda UV to a much lower scale M star, the composite sector confines and exhibits spontaneous global symmetry breaking G to some smaller subgroup H. And Higgs doublet emerges as a Lamborghini boson of this spontaneous global symmetry breaking. And when we couple the composite sector to the elementary sector, which includes all of the standard model gauge fields and elementary fermions, the interaction will explicitly break the global symmetry G and induce Higgs potential for these And another very important ingredient in composite Higgs is partial composites, and we rely on this to generate standard model fermion masses. And the idea is that at this very high scale lambda UV, in the interaction Lagrangian, we have terms in this form, which linearly couples the standard model fermion field to some fermionic operator coming from the composite sector. And this operator has the correct quantum number so that we can make a gauge singlet. And when we evolve the Lagrangian down from lambda UV to some lower scale M star, the Wilson coefficient will be suppressed by lambda UV to some power. The power is d minus 5/2. Here, d is the scaling dimension of this fermionic operator OF. Yeah, and so because we want to generate large enough top Yukawa, and to avoid the over-suppression of this coefficient, we will require the scaling dimension of this OF operator to be close to 5/2. Yeah, and in this sense, partial composite is more preferable compared to Technicolor way, in which we use Lagrangian terms which are bilinear in the fermion fields, because in this case the suppression power will be d minus 1. Here d is the scaling dimension of this scalar operator OS, and if d is close to 1, then we can form an operator OS squared, which will have the behavior similar to a standard model Higgs, and which will reintroduce the naturalist problem. So in this regard, partial composite is the preferred way. Okay. And I will talk a little bit about the effective field theory and UV completion, because there are a lot of studies in the literature which combines the idea of PNGP Higgs and partial compositeness in a low-energy effective field theory framework constructed by techniques like CCWD. And however, this construction is only valid up to some low cutoff scale and typically 10 TeV, and beyond which you will need a UV completion. And there on the market there are two popular choices of further completion. And the first one is called holographic completion, which is basically a 5-dimensional gauge theory defined on a truncated ADS spacetime. And this by ADS CFT correspondence, this will correspond to in 40 pictures some CFTs broken in the IR and also explicitly broken in the UV. And because of its extra dimensional nature, this holographic completion is non-renormalizable, and it should be UV completed further, for example, into some string theory setup. And another choice of completion of the PNGP Higgs Lagrangian is called fermionic UV completion. And this means that beyond the standard model gauge groups, we've introduced a new gauge group called hypercolor and some new fermions called hyperfermions, which are charged under this hypercolor group. And the hypercolor group will confine at low energy. And the PNGP Higgs arises as bound state of the new hyperfermions. And also, in this setup, we need to realize partial compositeness. And here, this OF will be composed of three hyperfermions. So, in this fermionic UV completion setup, the partial compositeness is realized by 4 fermion operators. And however, you know that 4 fermion operators are still non-renormalizable, and it should be UV completed further. And a very straightforward consideration is that, for example, if you can consider to UV complete the 4 fermion operator by some gauge boson mediator, massive gauge boson. Yeah, and this massive gauge boson might come from a partially unified gauge group. And so you might want to build a partially unified gauge theory, which when the gauge group breaks, it will automatically deliver the massive gauge boson and generates the 4 fermion operators that you want to have in the fermionic UV completion. And this is what we attempt to do in this work. And this partially unified theory is still not, strictly speaking, UV complete yet, because we will need too many fields, and so finally it should also be further UV completed into some string or quantum gravities stuff. Yeah. And in the literature, this fermionic UV completion has been studied a few years ago, and the basic model building game is that we want to enumerate all the possible hypercolor gauge groups and hyperfermion representations in which at low energy we can deliver PNGP Higgs boson and realize partial compositeness at the same time. And the model building constraints includes, for example, you need to allow the existence of top partner, which is a hypercolor singlet and has the correct standard model quantum numbers. And also at low energy, the theory should be non-conformal. Yeah. So taking into account of all these constraints, you can enumerate all the possibilities, and the number of solutions is essentially finite. And for the minimal case, they are categorized into 12 classes. And you can see, for example, this is the type of hypercolor group. We have SON, SP2N, or SUN group, and we need at least two types of hyperfermions, because for one type, it is responsible for the electric part to deliver the PNGP Higgs, and but for top partner, because it carries QCD color, so we will need a second type of hyperfermion, which accounts for the QCD color degrees of freedom. So this is the chi hyperfermion, and you can do the group theory exercise to check that all these models contain the appropriate top partner candidate, and also also estimate the lower boundary of the conformal window to check that best, this model should confine at low energy, and we get all those 12 classes of models. And then, because I have said that all these 12 classes of models, they realize partial compactness still via 4 fermion operators, which are non-relocalizable. So in our work, our task is to UV complete these 4 fermion operators. So we want to choose a simple starting point, and it turns out, because actually the full model construction is quite complicated. Let me first give you actually the outcome of the model structure. Yeah, at 100 GeV scale, which is the electroweak scale, of course we should have the standard model Higgs, standard model fermions, and gauge bosons. And then the next important scale is 10 TeV, which is the hypercolor condensation scale. And like hyperfermions and composite resonances, they also live around at this scale or below this scale. And we also have some PNGB and additional vector-like quarks, which are predicted from the unified structure of the model. And then very importantly is that from this 10 TeV up to 10 to the 16 GeV scale, we have a very long RG time for the strongly coupled near conformal dynamics. Namely, the hypercolor group is in its strongly coupled phase. And above the 10 to the 16th GeV scale, the hypercolor group and the standard model color group, they are unified into some larger gauge group. And the unification actually takes a few steps, and we call the intermediate group, the CHC group, EHC group, and eventually the technique Hati-Salam group. And about 10 to the 18th GeV, the model should be UV completed further into some quantum gravity stuff.
Sorry, once you have the intermediate scale, like the gap scale, does it cause another fine-tuning program?
Oh yeah, I need to mention that because here elementary scalars are only introduced at this very high scale, namely about 10 to the 16 GeV scale. So because the elementary scalars are very heavy, so we don't worry about their tuning. And below that scale, we don't have elementary scalars. So yeah.
But there is one physical scale, right? Like gap scale. So
you mean this scale?
Yeah, there must be some contribution to the Higgs mass, for instance.
So because Higgs is a composite, so yeah.
But you have also the option for the partially composite Higgs models. In that case, you have the elementary Higgs as well.
Here at low energy, we don't have elementary Higgs.
Okay.
Yeah. Okay, and we choose the model M8 as the starting point. The M8 is defined by a SP4 gauge group and with 4 wild fermions in the fundamental, 4 wild hyperfermions in the fundamental of SP4, and 6 wild fermions in the 2-index antisymmetry of SP4. Yeah, so for example, the top partner will be composed of 2 fundamental and 1 2-index antisymmetric guy. Yeah, and we choose this as the starting point because we checked that this M8 model allows a very simple embedding, namely when we try to unify hypercolor and the standard model color, it allows that we unify the fundamental of hypercolor and the fundamental of QCD color into the fundamental of a larger unified gauge group. So this is the most simple choice. And the examination of quantum numbers suggests that the simplest unification option is to unify SP4 hypercolor and SU3 color gauge groups with hypercharge into some SU7 group times U1 factor. So this SU7 will be called extended hypercolor. And we found that miraculously, by carefully choosing quantum numbers, the whole theory can be made anomaly-free with top partial compositeness mediated by a massive vector from this EHC breaking. And there are 2 hints at a higher level of unification to SU8 Hati-Salam group times SU2R. So this will be called technical Hati-Salam unification. The first hint is that lepton masses are left unexplained at the SU7 level. And the second hint is that the miraculous anomaly cancellation might be better understood. Yeah. And so let us try to do the model for the third family fermions alone. Yeah. And the fermion field content is as follows. And we have this omega field, which is fundamental of SU8 and the doublet of SU2L, singlet under SU2R. And we have this upsilon field, which is anti-fundamental of SU8, singlet under SU2L, and the doublet under SU2R. And we have this C field, which is this is the 4-index antisymmetric of SU8, which is a real representation. And we have also introduced some singlet field, which accounts for the neutrino mass generation. And from this table, we can see that the fermion field content is manifestly anomaly-free. And we can see also directly the field embedding. For example, this LT, LB, UB, DT, they are fundamental of SP4 hypercolor, and this TL, BL, ER, TRC, they are QCD color triplet, and we have one component for lepton. And in this C, we have this UTDB, they are also in fundamental of SP4 hypercolor, and chi tilde, they are in the 2-index antisymmetric of SP4, so they play the role of this guy. Yeah, and when we decompose this B tilde, we also have some additional field which are interesting phenomenologically. And this is the nasty part of this model building, because we need to introduce scalars for multiple reasons, and most importantly, we need to break gauge symmetries at high energy. Yeah, so we found that we need to introduce at least 4 types of scalars. Yeah, with representation listed here, and they allow us to introduce Yukawa interactions, and these scalar field they have the singlet component. When it gets wet, they can realize the various steps of symmetry breaking, and also important that they can also contribute to scalar mediated partial composite in these 4 fermion operators. Yeah. And let us take a look and have a feeling of the vector mediated partial composite in these 4 fermion operators. And the quantum number notation is as follows, and the most important is for this, I use this notation for the SP4 hypercolor, SU3 color, and the U1Y hypercharged quantum number. And if you do the index decomposition for this partially unified gauge theory, you can find that there exist 2 massive gauge boson mediators with these quantum numbers. And this guy is responsible for quark partial compositeness, and this guy is responsible for lepton partial compositeness. And for example, let us take a look at these 4 fermion operators. And it is composed of this DT bar, TRC, chi bar, eta, and you can take a look at this table. And for example, this massive gauge boson from SU8 breaking, it will connect this DT and the TRC, and it will also simultaneously connect chi and eta here, and give you the desired 4 fermion operators. And all the vector and scalar mediated PC4F operators are generated automatically instead of being put in by hand. And okay. And finally, I want to talk about one interesting theory consideration, because eventually we need to extend the model to account for all 3 families. And so for the fermion field content part, and straightforwardly, we need to copy for example, these fields, n omega epsilon 3 times. We don't need to copy Cassi for 3 times, because Cassi does not involve stand model fermion field. And when we copy the fermion field, and then the most important thing here is the masses of the hyperfermions. And the hyperfermions, they are highlighted here. Yeah. And for the 3rd family case, and also the hyperfermions in Cassi, yeah, they are required to be light because they are responsible for partial compositeness. However, for the hyperfermions in the first 2 families, we found that it is preferable that we make them to be super heavy as 10 to the 16th GeV scale. And this is preferable when we consider that we require the theory to enter into a strongly coupled near conformal dynamics between 10 TeV and 10 to the 16 GeV. Yeah. Okay. And then the important thing is that actually, well, we can generate masses for the 3rd family using just the vector mediation. But however, for first and second family, we found that it is impossible, and we need to rely on other mechanisms. And the reason is related to this simple question. For example, let us consider in pure QCD, does there exist non-vanishing flavor-changing condensate, say, this TC bar condensate? And the answer is no, because according to a theorem by Baffa and Witten, non-chiral global symmetry cannot be spontaneously broken in a vector-like gauge theory. And the question is, what about the situation in full-stand model? And the answer is probably no, because otherwise we will have violation of the 't Hooft decoupling condition. Yeah. And in this model building case, and for example, if we want to generate masses for the second family, we need to break both the ZL2 and SU2 and L2 symmetry, which is defined as some Z2 parity and SU2 rotation on the left-handed fermion field, omega. And we check the symmetry properties of the interaction. We can find that if we don't have family-changing Yukawa interaction, and all these interactions will preserve these symmetries. And so in that case, if you want to generate the second family fermion mass, you need to spontaneously break ZL2 and SU2 L2, which will lead to violation of 't Hooft decoupling condition. And so our conclusion here is that to generate masses for the first and second family, we must introduce family-changing Yukawa couplings, and to realize partial compositeness by scalar mediation. And finally, I need to mention open issue is that the suppression of unwanted flavor CT violation, because although the flavor scale is around 10 to the 16 GeV, flavor and CT violation are incorporated into local PC4F operators whose effects are preserved down to 10 TeV scale. Yeah. And you might have a lot of questions which I have no time to discuss. But finally, I just want to mention that the lattice calculation is expected to play an important role in testing the validity of the models. And thank you for attention.
Sure. Any questions?
Yeah.
Is it easy to reproduce the 125 GeV Higgs?
The issue is that I think currently in this model it's difficult to make prediction for Higgs mass. Yeah.
But can you reproduce?
Well, but in general, I don't see obvious obstruction. Why 125 GeV cannot be reached? Yeah.
And there's only one Higgs. And at this scale, how many scalars? Particles.
Yeah, the model
100 GeV.
generically predicts additional Higgs bosons.
Only one.
No, there are
Additional.
additional PNGV Higgs. Yeah, because the concept is larger.
Since we run out of time, I leave for later discussions. Okay, thanks, Dr. So next speaker is Krishna. Krishna is okay. So we are talking about the phenomenology of G2 HDM models.